So this is the world of atomistic simulation, and Antoine will introduce you to this world. And at the end, if you want to stay with us and ask questions, you're more than welcome. And again, I want to thank first my student to put all this effort to have a professional research and workshop day. I think they did fantastic. I'm sure that if there are industrial partner or industrial people here, you might be interested in hiring these fantastic candidates. That's also the reason why I wanted to have this workshop done. And don't hesitate to contact them and interact with them. So thank you so much for attending this long day. Maybe you'll be able to see each presentation that you want selectively after in the future. And again, hoping to see you in the future for another FactSage workshop. So Antoine, you can go for your presentation.
Jeff, do you have a question about MedSim?
Oh, sorry. Yeah, so we'll be able in MedSim, yes. So in MedSim, we'll be able to use all solution or compounds. So all the faces that will be selected in FactSage will be able to use it in MedSim, and that's the reason why we did that. So for the slag and for all these important solid and liquid solution, of course, they are considered. So you didn't really look at the interface completely, but we still need to work a little bit on the definition on the MedSim side of solution and compound, which is not as clear as what we have in FactSage, but we're working on that. But yes, all the same kind of faces will be available. So you can go, Antoine.
All right, thank you very much. Can you hear me well and see my screen?
Yes.
Yes.
Perfect, awesome. So yeah, so I'll be presenting molecular dynamics. I know it's the end of the day and we're pretty much all tired, so it's a much more relaxed and chill presentation, so I'll just introduce you to it without going too much into details, but I'll still explain a bit of everything. Speaking of which, I'll go straight to my presentation plan. The goal of my presentation is basically to explain to you the what, why, and when of molecular dynamics, how they work, and give you a quick introduction as to what you need and what you will get from them, and then give you a commented example, all the files from which are available on the workshop's website. Alright, so let's begin with molecular dynamics and their introduction. First off, you need to know the scale. Scale goes both as a function of time and a function of dimension. So this figure is really basic, it's not precise, it just to give you like a rule of thumb as for the dimensions and time that you can do with different types of simulations. In this case, we're talking about molecular dynamics, so it's the little L that represents lamps in the middle that we're interested in. Other projects that we've seen today, such as Javier's work with DFT, which is much more precise. However, it's you can only simulate much smaller systems for a much shorter period of time. You can also use Monte Carlo, which we don't really do, which will be able to simulate bigger systems for a much longer time. However, it won't be as precise. So it's always, like most things in engineering, basically, a compromise between what's best and what you can afford. The main point with lamps is that it's parallelized. It's made to be used on supercomputers, so you can launch really big simulations despite it being molecular dynamics, like the grains that I presented during my presentation earlier today. So this graph is to give you a quick idea of how the performance of the molecular dynamics simulations will scale as a function of the number of processors you give it, should you ever need it. Alright, let's talk about some examples so you know a bit more about what I'm talking about when I'm talking about lamps. So here are some more examples towards metals. First off is an example of an ultra thin copper wire formation, so I'll just let it go and do its thing. So as you can see, the simulation is able to create the copper nanowire through the strain and stresses in it. Another example is the formation of helium bubbles inside of a molten metal. And so we can evaluate the impact of those bubbles. However, you're not forced to use lamps for everything that is molecular dynamics. You can also use it for the discrete element method, which if you know what it is, you'll understand why it can be used with lamps. It's because lamps simulates atoms, which can be used as discrete elements for the discrete element method. I did that in a project simulating the Brazil nut effect, which you might have heard about because it's a pretty common problem. Alright, now let's talk about how molecular dynamics works. So here's the basic cookbook to a good molecular dynamics simulation. The first part is the Newton's equation of motion. Basically, at each time step, your atoms have forces applied to them either from their position towards compared to other atoms, or their initial speed, or anything really, like the temperature for example. From those forces, we compute the velocities in the 3D space of each atom, with basically F equals ma. From there, we'll use a Verlet time integration to see from their position and their velocities what will be their newer positions. The reason why it uses a Verlet integration is because the Verlet time integration is symplectic, which means that it will ensure conservation of energy and won't either create or destroy energy like other time integration methods could. Then, once that's done, each CPU that is working on the simulation will share its information with one another in order to make sure that every CPU knows what's going on in the entire simulation. In the case where you're doing a simulation on a single core, you won't need that step, but that's really extremely rare. And finally, from all the positions of your atoms in your lattice, with the interatomic potential, you can compute the forces as well as the thermodynamic properties, such as the enthalpy, for example. Speaking of those potentials, the potentials are basically the one thing that makes or breaks your simulation. As we say in mathematical models and simulations, garbage in, garbage out. If your interatomic potentials are bad, your results will also be bad. However, if your potentials are good, you can hope that your results will be good. So here's an example of basic potential. No, go ahead, sorry.
No, we missed your microphone, but now it's good.
Okay. I'll increase the gain, sorry. So yes, as I was saying, interatomic potentials will make or break your simulations. And as we say, garbage in, garbage out. So if your potential is bad, your results will be bad. However, if you have a good potential, you have a good hope that you will get good results. So here's an example of a basic potential which odds are won't get great results. The Lennard-Jones potential. As you can see, it only has 3 parameters, and it's really basic. It won't account for a lot of things that would really happen in such a huge scale as you would have in molecular dynamics. So to get a rough idea, you can use that, but it's not really useful. But a more complex potential would be the modified embedded atom model, which has a lot more parameters and considers a lot more forces. From that, well, you can intuitively imagine that you will get ideally better results, assuming that each of those parameters are better. There are tons of different potentials, and all of them have different perks and downsides. It's really down to what you want to simulate that you will need to pick the right type of potential for you. We mostly use the modified embedded atom model here because this potential is really good at working with metals without being too computationally intensive. So it's the perfect potential to work with. Now that we all know this, let's talk about some sample outputs. So the most basic of outputs is the thermodynamic data. You will get this in your simulation as it goes on. Basically, it just gives you the information about the state of your simulated system. The block of text, or numbers as it would be better to say, that you can see at the top of the screen is what you would get in your simulation in the command window. If you plot it as a function, say enthalpy is a function of the time, then you can see how it evolves, and as you can see from the graph, even though there are some fluctuations, it's mostly at an ergodic state, which means that it's the average at any point is roughly equal to the average of the entire sample. This is what you want to get in a simulation because this is what will indicate that your simulation has reached equilibrium. Then there's computed data, which is given in lamps from compute commands. These will not be given unless you call for a compute command. An example of this is for the radial distribution function, which gives you information about how the different atoms are placed relatively to one another in your lattice. So what you get is actually the string of numbers that you can see at the top of the screen. And if you plot them, for example, the radial distribution function as a function of the radius, well, you get this nice curve that is really much more interesting, and you can get information from that. Finally, the more common type of output you will get is dumped data. So these data are really, really big. It can go in the hundreds of gigabytes per files if you have extreme cases such as the grain defects I had shown you in my presentation earlier. What this does is it contains the information about every atom you have. So if your simulation has 4 atoms, it will be a really small file, but if you have millions and millions of atoms, then it can get really big really quickly, because each line represents information about 1 atom. So in this example, what it gives is only the idea of the atom, its type, and then its coordinates. You can also make it give, for example, the velocities. So this way you could plot not only the positions, but also the vector of the direction they're going in as a function of time. It's not always useful to do that, however, which is why I'm not doing it, because it would increase the size of the files that I need to use, which are already pretty big. So now that you know a bit more about simple outputs, let's give you a quick, not so simple starter example. So in this case, we'll be trying to plot the melting curve of pure aluminium using molecular dynamics. So we'll do this with multiple simulations that will each call upon one another. The first one goes like this. So first off, you initialize all of your variables and then initialize the simulation, so that way your simulation knows at what temperature to run, for example. Then you create your atoms. So this is basically your system. In this case, 4,000 atoms is enough. I found that 4,000 atoms for this kind of simple simulation is a high enough number to reduce the impact of noise, but not big enough that it will slow down your simulation that much, and it can be run on your own computer, which is why I gave this as an example rather than something more complicated. Once your atoms are created, you can define your interatomic potential, for example the MEM potential I had spoken about earlier, and then you just run your simulation. So in this case, all we do is we just leave it at a given temperature for a long while and see what it gives. After that, just print the information. And then the file afterwards, we'll just call upon that last simulation, heat it up a bit more, and then equilibrate again. The idea here is that every simulation will reach an ergodic state, sorry about that, and from that ergodic state, you can plot the enthalpy as a function of temperature and see where the melting actually occurred. Let's look at that. Alright, so all of your simulations are run, you plot enthalpy as a function of temperature, what do you get? This curve. So as I've told you earlier, the little jump in enthalpy that you can see at the end of the blue trend line is indicative of melting, of phase change. Actually, it's the simple phase change. The reason why it isn't above and the last blue point doesn't reach the orange line just means that the simulation, even though it was ergodic, was not long enough to force the enthalpy to reach the same as the actual liquid. But the following simulation did reach it. So we actually know what the melting temperature is. It is the temperature at which this jump occurred. If we look at the radial distribution function of that last simulation, you can see that at the start it's somewhat like a solid, whereas at the end it's somewhat more as a liquid, which confirms what we believed. You can then look at the dump output of this and see that actually it is indeed melting during the simulation at some point. So we now have the confirmation that the simulation did melt like we were hoping it for. So we now know this. Now you'll notice that for pure aluminium, 1141 Kelvin is quite high when we're actually expecting 933 Kelvin. And this is because it's a perfect lattice. If you'll remember my presentation from earlier, this means that it will estimate the melting temperature to be much higher because it will estimate the thermodynamic melting temperature rather than the mechanical one. So we can use a formula found in the literature, like this one, to convert it, and now see that we reach 927 Kelvin, which is much closer than what we had before to what we were expecting. So I hope this was clear. If you want to learn a bit more or explore it by yourself, I know this was quick, it was just meant as an introduction. All the necessary files are available on the workshop website with the bit.ly link you can see below. I can send it in the WebEx chat if you want to. And I hope this was very helpful to introduce you and to create an interest in molecular dynamics. So thank you very much for listening, and I hope you had a great day and a great workshop. Thanks.
Thank you so much, Antoine. So now I think we can unlock the tie. We're done. The summer is done. Let's have some